All right, so today we're supposed to be doing a recitation, and I think the recitation, probably the main topic that many of you are interested in is looking at that second problem on the homework, okay? And I do want to introduce a few sort of lecture-like stuff, some of the simpler things having to do with the NumPy and the Matplotlib modules that you'll need to solve that that homework number 2. Okay, so before we get speaking directly about the homework problem, we'll get to that. But why don't we go ahead and do a few things having to do with NumPy and Matplotlib. Okay, so if you want to plot something, okay, you will need to use Matplotlib. Now, Matplotlib is actually enormous. There's a whole bunch of sub-modules in Matplotlib, and the basic one that we're interested in is called pyplot. Okay, pyplot. Just like NumPy, we can import that as something. Okay, you'll recall we would often do NumPy as NP so that we don't have to type NumPy all the time. I can just type NP. Okay, now it's pretty standard. Most people write NP. They import NumPy as NP. I don't know. I'm a little torn here because most people import matplotlib.pyplot as PLT, which I don't know. I personally like to call it plot. Now, I don't know if that makes me a conscientious objector or what, but I tend to like to call it plot instead of PLT. I don't know. That's sort of what I've gotten used to. So that I'm going to go ahead and do that. But remember, you can make this thing here be whatever you want. You can make NP be whatever you want, whatever makes the most sense for you. Okay? But like I said, a lot of people are going to do just PLT there. Okay. So what's really amazing about Matplotlib is that it's almost totally hacked from MATLAB. Okay? And I'm pretty sure I have put the link to this on D2L. But if you go to matplotlib.org and click on pyplot, it gives a list of all of the different commands, and you'll recognize a whole bunch of them: bar, CLF, contour, figure, GCA, GCF, CLF, IMRead, IMSave, and then of course the good old plot command. Okay, so all the commands basically have all the same names as MATLAB, and they've tried as much as they can to make the syntax the same as MATLAB. Okay, which is really great. So if you know how to do MATLAB, you basically already know how to use the pyplot part of Matplotlib. Okay, so for example, if we wanted to plot something, we would use the plot command, but just like if we use a NumPy thing, you need to put whatever you name, whatever you import that module as. So this plot right here is the same as that plot. So this one here is the name that we've loaded the module in as. Okay? And then this is the command we want to call, which happens to be the same as the name of the module, the way I've imported the module. And the way this works is you send two arrays, one array with the x values, one array with the y values. Okay? And then the third input argument can be a string with the color or the shape of the line that you want it to plot. Sounds familiar, right? Okay? So I could hard code something in here, 1, 2, 3, 4, 5, and let's do 1, 4, 9, 16, 25. And I need to save this somewhere. So I just hit Control S so I could save it. Go ahead and put it in my work directory. Come on, where is it? Here we go. Spring work. Sure, we'll just call it Untitled 0. Okay, so I saved it, and now I'm in the IPython console down here, and I hit play, and there you go. There's my nice, pretty plot. Let's see, how do I make that bigger? Here we go. Okay. And so it's blue because I put B, and it's a dotted line because I put the colon. It works just the same as MATLAB does. Okay? Now, you'll notice that this is technically a Python list. So I can send a list of things and another list of things. Okay? It also accepts NumPy arrays, which is actually more useful. Okay? Because, for example, you'll recall if I define that as x and then try to say y is equal to x squared, for example, okay, that won't work. When I try to run that, okay, there is no power operator for a list. Okay? Because you remember, the list doesn't have to have just integers. It could have strings in there, and it could have arrays as lists, or can have lists as the elements in the list. Okay? So if we want to do something like this, we need to make this a NumPy array. So NumPy has a command called array, where if you pass it a list of numbers, it will convert that into a NumPy array of numbers. And then I'm pretty sure, I can't swear by it, but I'm pretty sure the power operator is an element-wise power operator. Okay, which it is, I think. Because 5 squared is 25. Here's 5 squared, 25. 1 and 1. Yes, Rusty?
You said this a white space doesn't matter, so you have to use commas?
Yes, in the white space, you can't put spaces in here. You can't put spaces like you can in MATLAB. In MATLAB, you can put spaces or commas. You must use commas in Python. Okay? So I guess that's a good reason for why I should break my habit of using spaces in MATLAB and only use commas there, so that it would be more portable. Okay? So this is really cool. You can do all sorts of, you can do a plot, and the plot command works just like it does in MATLAB. Okay? You can use the CLF command, works the same essentially. The figure, if you want to open a figure. If you want to hold it on, let's see if I want to do y2 equals np sine of x instead, and I wanted to plot two things, I could do plot.hold, and the way that works is you pass it a boolean of whether you want it to hold or whether you want it to not hold. Okay? And then I could do plot.plot xy2 and make that black and be a solid line. Okay? So now I've got both of them on there by holding the figure. I haven't checked. I'm not sure if you can pass multiple lines. If I could have put this in here, I wonder. I don't know if that will work. It works in MATLAB. Looks like it works here too. Big surprise. Works the same as you do it in MATLAB. So you don't have to use the hold. You can pass multiple things to a single plot and have it plot. Okay. All right. So that's basic stuff of how to plot things, because you're going to need to plot some really simple lines for the homework. Okay. I also wanted to go over a little bit about NumPy and show how you can use logical indexing and use the where command, which is just like the find command in MATLAB. That might come in handy for you in the homework. Okay. So you know what? I may just go ahead and do that in the command line here. So I'll define x. I'll define x as, and what do you know? There is a linspace command in NumPy. Okay, so and it works the same. What's the base value, first value? What's the second value? And how many things do you want? Okay. Now, unfortunately, pi. I need to import NumPy. Unfortunately, pi doesn't exist in itself in Python, but NumPy does have a definition for pi. So if you want pi, you can access it through, it's a constant in NumPy. So np.pi will give you pi. Yes?
So, like, question. You have the hashtag include all this stuff. Can we put the import numpy link in the very top before version 1 that won't affect anything problem 1?
So you're talking about the import stuff?
Yeah, but we
yes.
Higher in the homework wouldn't matter.
Right. So just like I think you can put the function definition anywhere in your script, I'm pretty sure you can put the import anywhere in your script. And so if you're using NumPy for problem 1 and problem 2, you only need to import it once.
Correct, but it won't affect anything problem 1 because you don't use it.
No, it won't affect anything if you import it and you don't use it in problem 1. That's true. Okay? So now, for example, the length x is a 100. And what is the type? That's an interesting thing to ask too. It is a NumPy array. Okay? So linspace returns a NumPy array. Okay? So now we have x as a whole bunch, 100 different values between 0 and 2 pi. Okay? I can say, for example, x, you know what? Let me redefine that to be fewer. Let me redefine that to have only 10 values. So now there's only 10. Okay? I can say x greater than, say, numpy.py. Okay? And so this is going to return a NumPy array, but where the data type of the values in the array are Booleans. Okay? So the first value is not greater than pi, second is not, third is not, fourth is not, fifth is not. The sixth value is greater than pi, the seventh, eighth, ninth, and 10th are all greater than pi. Okay, it works the same way you would expect it in MATLAB. Okay? And then I can do logical indexing just like I can in MATLAB. Give me all of the x values where x is greater than pi. Okay? Those are all of the x values where x is greater than pi. Okay? Works exactly the same way as MATLAB. Isn't this really cool? So, you know, if you're fluent in MATLAB, you know, it's not very much to pick up how to use NumPy and Matplotlib. I mean, they purposely created Python to be that way, you know, because they knew how great MATLAB is. And it's really quite amazing. I mean, for me, as such a MATLAB proponent for so many years, I'm starting to think, well, Python did it just as well and then has lots of other stuff that are great. So I'm almost, I'm sad that I am not such a great proponent of MATLAB anymore. I like Python better. Okay? So we can use logical indexing in this way. Okay? We can also search the array to find values and return the index positions where something is true. And that's the where command. So for whatever reason, they didn't call it the find command like they do have in MATLAB. Okay? So the NP, the NumPy where, and what you pass to it is just like you pass to find. You pass to it an array of Booleans. And it will return you the index numbers where those Booleans are true. So if I say x greater than np.py, okay, it returns to me the 5th, 6th, 7th, 8th, and 9th indices are greater than pi. That's 0 index, 1, 2, 3, 4, 5. The 5th index and then 6, 7, 8, and 9 are all greater than pi. Okay? Works very much the same. Okay? Now, one of the really weird things here is what has it actually returned. I mean, we can look there as a human and see, well, it's the 5th, 6th, 7th, 8th, and 9th. Okay? But what is the data type and how is that actually organized? And it's kind of weird. Okay? And this is what I've said, this has been my biggest struggle learning Python, is understanding what data types you have to pass to things and what data types are returned to you. And you might not realize here, but this is actually returning a tuple. Because if I say, let's say I do ind equals this thing, and I store this thing in ind for index. What is the type of ind? Ind is actually a tuple. Okay? But it is a tuple of length 1. Why on earth would I put this stuff, there's an array that is inside a tuple? is what it actually is. You can see, and actually you can tell with these parentheses, you can see that it's actually a tuple, and there's an array inside of the tuple. So that's really strange. Why on earth would they put this thing inside a tuple? Okay, and the reason is because I could have a multiple dimension array. Okay, so for example, instead X could be my favorite two-dimensional array. 1, 2, 3 in the first row, 4, 5, 6 in the second row, 7, 8, 9 in the third row. Okay, so now, oh, but that's actually a list. I want that to be a NumPy array. That's a list. I need it to be a NumPy array. So now X is a NumPy array, and you can see it's kind of interesting. When it's an array, they actually draw it like a matrix. They draw it like a two-dimensional thing. That's how I realized I did the wrong thing when I did it there, that's a list. This is now an array. Okay? And so if I now did end is equal to NP where X is greater than 4, okay, and look at what end is. See, now it's like the same thing you would do in MATLAB when you have a matrix. These are the row positions where that thing is true. These are the column positions where that's true. So they're sending you a tuple of arrays of index numbers for row and column. In MATLAB, it would have returned two variables. It would return a variable of the array of X positions and a variable of the array of row positions. So for whatever reason, NumPy has decided I only want to return one thing rather than two, and that one thing I'm going to return is a tuple containing the two arrays. Okay, so when I did the where here, let's see, where was that? Here. When I said end is equal to that where, okay? X in this case is a one-dimensional array, okay? And so what it has returned for me in end, the first thing in the tuple is the row position, and there is no column position. So they still put it in a tuple because they're allowing for the added flexibility that it might have a row, comma, column. Okay? So it's a little weird. All right? So, for example, if I wanted to get out of here, what is the first position? What is the first row where, well, let me do it this way. Rows. The rows where that is true is the first value. No, tuples are indexed with square brackets. Okay, so rows, that pulls out the first value in the tuple. It pulls out the oh, I want the zeroth. Darn it. Okay. So end 0 will pull out the 0th index in the tuple, which are the rows. First row, well, row index 1, row index 2, row index 1, row index 1, row index 2, 2, and 2. Okay? So now rows is an array of the rows where that is true, and calls is end 1. That's an array now of the columns where that is true. Okay, so if I now wanted to pull out the values out of X, I could say, give me the first row and the first column where that is true. All right, what did I do wrong? Rows. I called it rows and calls. So my original X was this. You'll recall that my ends I got where I was asking, where is X greater than 5? Okay, so this one, and those three are greater than 5. So rows has all the rows. That's row index number 1. So that's here, this row. There's 2 things in that row that are greater than 5. There's 3 things in row index 2 that are greater than 5. And calls, okay, that's saying row index 1, column index 1. That's the 5. Okay, row index 1, column index 2, that's the 6. Row index 2, column 0, that's the 7. Then 2, 1 is 8, 2, 2 is 9. And so if I wanted to extract them out, that's what I've done here. That says, give me the very first row and column where x is greater than 4, that's the 5. Give me the index number 1 row and column where x is greater than 5. That gives me the 6. Then I can get the 2 and the 2, etc. Okay? So what's kind of weird, you remember, is that end returns a tuple with the row column. Okay? And if I want the rows, I need to get the 0th index of the tuple. If I want the columns, I need the first index of the tuple. So let's go back to what we were trying to do before. Yes?
Is there a not function?
A not?
Yeah, like not.
I'm not sure. Let's see.
There's a logical difference.
There has to be, but I'm not sure what it is. In MATLAB, it's tilde q.
You can literally type it.
But that must have done something different. I'm not sure, Rusty. There has to be. Let's look at NumPy logical negation. Logical not. Just like logical and logical or. So logical not seems to be that command. So if I take np logical not q, that should give me true. Okay? Now that should also work if I have true, false, false, true. That should work. That'll work on a list or an array of things. Makes the true to false, makes the false to true, false, true, true to false. What's that?
It's an inverter.
It's an inverter. That's exactly right. Okay? All right, so let's go back to what I was trying to do. I've got my x, and I then say, give me the indices where x is greater than 3. Okay? Oh, I want to do where. Give me the indices where x is greater than 3. Okay? So that's the 0, 1, 2, 3, 4, and 5 index are where they're greater than 3. And so if I wanted to get me the first one, I would first have to index to get the first thing of the tuple, and then the first one in that array. So I could do it all in one line if I wanted, or I could say real index equals ind 0, and now real index has 3, 4, and 5, and real index 0 is the 3. That's the third position. And then if I said give me the x position of real index 0, that gives me the 4. Which is, of course, the same thing as doing this, where I can do it all in one fell swoop. So it's a little bit weird handling the tuples and the lists and the arrays, but at least the concepts of what you're doing and how you do logical indexing and finds and all that sort of thing is basically the same as MATLAB. And the reason I'm introducing this is because it depends on how you solve the problem, okay, for the homework. I personally, there's these 4 different cases, and I personally put the distances in those in an array of values and searched them. But there's only 4 things, and if you really wanted to, you could do a whole bunch of if-else stuff if you really wanted to, and you could get by with that. But if you're wanting to be fancier and have your code be more compact, you can use this idea of the logical indexing and all that if you wanted to. Okay? All right. So that being said, let's go ahead and look at the second problem in the homework again. Okay? Let me go ahead and pull that up. Yes, question?
For submitting the homework, you want to have it set up like MATLAB?
Right, so submitting the homework, you're going to submit to me, you're going to upload a single .py file that has both pieces in it for both homework problems.
Okay. You just want to set up like one function for problem one and then.
You can make them functions. You don't have to.
Okay.
Because in Python you can mix scripts and functions, which you couldn't do in MATLAB.
Okay.
But you're welcome to if you want to. You can set it up as your main name of your thing be a function. I mean, you still actually have to call it somewhere, but it doesn't matter to me as long as I get a single file, a single .py file, and run that. Then that'll be fine. Okay. All right. So in this problem, we've got this 2-arm robot. Okay, so these 2 links here represent the robot arm. And one end of the robot is always fixed to the 0, 0 position. So one end of the robot is always at the origin. Okay? Then we can make this robot move depending on what the angle theta is, which is how much the first arm makes with the horizontal. Okay? And what the angle phi is, which is what the second arm makes with the first arm's direction. Okay? And so we can move the end point here, which in a robot we usually call the end effector. We can move the end point of the robot all over in space by controlling what theta and phi are. Okay? So we can make that robot's end go wherever we want depending on what we put for the values of the angles of theta and phi. Now in this problem, you're going to be defining a start point that you want the robot to start at and an end point that you want the robot arm to end at. Okay? And what we want to do is we want to make the robot start at the start point and follow as closely as it can a straight line from the start to the finish. Okay? So we're going to have a loop that's going to loop through how do we move that arm. Now, of course, in a program, we're going to have to make that move in discrete increments. We can't make it, move continuously. So basically, our loop is going to go in discrete increments of moving that arm along the path from 0 to F. Okay? Now, basically what we're going to be looking at is when the robot arm can move, either we can increase or decrease theta, or we can increase or decrease phi. Now, of course, if it was more complicated, we could change both of them at the same time. Okay? But just for simplicity, we'll go ahead and look at only changing one of either theta or phi at the same time. And we have to make the choice. Should we increase theta? Should we decrease it? Should we increase phi? Or should we decrease phi? Okay? So this figure down here is an example of where this magenta line is the path that we want to follow. And we want to start here and we want to end here. And the green arm position is the position that the robot is going to start in because its end effector is at the start point. Okay? Now, in this green position, we need to decide, do we increase theta, decrease it, increase phi, or decrease it? Okay? Now, I've over-exaggerated how much those angles change. In your real program, you're going to want those angles to change a small amount. Okay? But here I've exaggerated so we can see what actually happens. This blue line is when I change the angle theta. This angle theta right here. Okay? If theta increases, then this arm rotates counterclockwise. Okay? So the blue one is where I'm starting at the green and I'm rotating counterclockwise. That means theta has increased from what it is for the green to what it is for the blue. And you'll notice that the angle between the blue, between the two arms in the blue is the same as the angle between the two arms in the green. That means phi did not change. Okay? So the blue one is where I'm going from the green to the blue by increasing theta and leaving phi constant. Conversely, the red one is where I have decreased theta but kept phi constant. Okay? So the red and the blue are two of the four choices we can make. Now obviously the red one's definitely not the right one. The blue one's better than the red one. Okay? But then we have two others to consider, and that's the yellow and the purple. That's the situation where theta stays the same, which means the first link of the arm doesn't change, but we increase or decrease phi. The yellow one is where we increase phi going from the green to the yellow. And the purple one is where I decrease phi going from the green to the purple. Okay? So of these 4 choices, which is the right one? Which one should we choose? Yellow, blue, purple, or red? Yellow's the better one. Blue's not bad, but if we're trying to follow the magenta line as closely as possible, the yellow's better, right? So both the blue and the yellow will get us closer to the end, but the yellow is following our desired path better. It's not exact. That's because the angles, the angles are some finite amount, okay? And so what would be a heuristic, a choice for how we would decide among these? Well, first of all, we can throw out the purple and the red. And it's an easy way to throw them out because these 2 end effector positions get me farther from the goal than where I was. Surely I should not choose to do something that makes me farther away from where the end is. So I can automatically throw away purple and red because they're farther from where I want to be than where I currently am. Okay? So then the choice is between the blue and the yellow. They both get me closer, but the yellow is closer to the line that I want to follow. And so if we were to measure the distance from the yellow end effector to the line and the blue end effector to the line, the distance between the yellow end effector and the line is smaller. So I should choose that one over the blue. So every time through my loop, I'm going to have 4 choices to make. I first of all throw away any that take me farther away from the goal. And of the remaining ones, I need to choose which one is closest to the line, the magenta line. And that's the one I'm going to choose. So in this case, I should increase phi. And then my loop will end, and I'll start over again. And I'll use the yellow position as my new current position. And look, what happens if I increase theta from the yellow, decrease theta from the yellow, increase phi from the yellow, decrease phi from the yellow. And choose of those 4 which is the best choice. Update either theta or phi, whichever one is appropriate. Start the loop over again. And I'm going to keep looping, keep looping, keep looping until I'm done. How would you know when you're done? What would be a good way to say whether the loop should end? Well, we're never going to exactly get at the end point probably, because these are going to be floating point numbers, and I can never say, is my value exactly equal to the end point? That's never going to be true, almost certainly.
Maybe we set a boundary.
So we could set a boundary. When am I pretty close to it? That's a good way. Any other suggestions?
Or we can less than -3 on the x-axis. You go to,
Well,
if the arm can reach that far.
yeah, I guess you're saying that if I go past it somehow and come back, that's another way we could think about it. There's actually a really easy way, because all these would work. The easiest way is if all 4 of the candidate positions take you farther away from the goal. That's really simple because I'm already calculating all these 4 positions, right? And if all of them bring me farther away, then I should just stop. So that's actually easier, and all the things you suggested would work fine. But that's actually the easiest because you're already calculating how far away you are from your 4 candidates. So that's a really easy way to stop. Okay? All right. So intuitively, we have the problem solved. Now we all know that that's the easy part. The hard part is making the program do what we've just described. So what I've suggested for you to do is to create several functions. Okay? Get point 1. And what point 1 is the joint between the first and the second link. Okay? So this is 0, 0. Okay? This is where point 1 is, and the end effector is at point 2. Okay? And so I've worked out all of the math and the equations for you. Okay? So in order to get point 1, I need to know the length of the first link and the angle theta. And then that will calculate x1 and y1 using these equations right here. Pretty simple, it's just trig. Okay? Then get point 2. That will return for me where the end of the robot is, the end effector is, the end of the second link. Okay? And in order to know where the end of the second link is, I need to know the length of the two arms. I need to know what theta and phi is. And then I can return x2 and y2. Okay? And here are the equations. In order to know what x2 is, I need to start where x1 is and then use this equation. To get y2, I need to start where y1 is and use this equation. Okay? So get point 2 is going to need to call get point 1 to know where x1 and y1 are. Because the things you're supposed to have as the input arguments for point 2 don't include x1 and y1. But there's enough information here to get that. To get x1, y1, you need L1 and theta, both of which get point 2 has. So the first thing you're going to need to do in your get point 2 function is to call get point 1 so you know where x1 and y1 are. And then you can calculate what x2 and y2 are and return those. Okay? Then I want you to make a function draw arm. And it's going to take the length of the two links, the current theta and phi, and where the initial and final points are. Okay? And the initial and final points are essentially defined here in this table. Here's xf, negative 4, 4. That's actually this point right there. This graph is based off of this information. So I'm telling you where the final point is. Now I haven't told you where the initial point is, but I've told you what the initial theta and phi are. And if you know what the initial theta and phi are, you know where point 0 starts. Okay, the end effector at those initial theta and phi are where it starts. So I haven't explicitly given you x0, but you can calculate that. Okay, so that x0 and that xf and the y0 and the yf don't change. Those, for this problem, you're going to use those two. You're going to make your robot follow this magenta path. Now, of course, once you're done, you can play around with it and you can change what the initial position and the final position are and see how well your robot can follow. But for this problem, you only need to do this one magenta line. Yes?
Is there a recommended amount to change the angle?
A small amount that doesn't take up too much time.
What again?
Okay, it's one. You want it lagom. That Swedish word for just right. Okay, if it's too big, you'll be jumpy like this, and you might jump around. You won't follow that magenta line very well. Okay, and if it's too small, it will take forever to run your program.
But it'll be a steady system as long as it
And it would be
down.
right. So ideally, you want the limit as the steps in theta and phi approach 0. And then you would have a continuous motion. Okay? Now, I gave an example down here. Here's the example of how I had it go. And you can see, the blue are all the points that it traveled on. Okay? And you can hardly see the magenta line because it traveled it pretty smoothly. But you can see here it doesn't exactly follow, it's curved a little bit. Okay? And I don't remember what I had. I don't know, maybe it was a fraction of a degree or something like that. I don't even remember. Okay, but I started off with a relatively large one to see how it was going to make sure everything worked, and then I decreased it until I could see, get what I wanted. Okay, so I'm purposely leaving that ambiguous. I, choose what is appropriate for the step size. Okay. All right. So the start and the end position. Okay, the draw arm, what the draw arm should do is it should draw your the two positions. It's going to need to find where x1 and x2 are and then draw your little robot arm. Okay, and then I guess I didn't say in here, I guess if you're passing 0 and F, you can also draw the magenta line. Yeah. In the end, I don't really care exactly what their final graph looks like. I just need to see that it's moved. If you want to do something like this, you can. An easier way to do it is to have your draw arm draw not only the arm but also that magenta line. And then if you do hold on, you'll see all of the different arm positions. Okay, which would make the graph a little cluttered. I was a little fancier and made it so it only drew the end point and didn't draw the arm and only drew the final position of the arm. But I don't really care exactly what this looks like. I just want you to go ahead and make it so the arm will make that transition and that I can see that. So I'm not really picky about what your final graph looks like.
How do we draw the table, or is that something?
How do you draw the table?
Yeah, like how would...
Which one? Which table you mean?
Like to put the line and the magenta line on there.
You could use the hold on part,
Okay.
you know, like we had done, where you can, you know. So why don't we go ahead and make a draw arm function? That's not what I wanted to do. So let's go to Spider here, and instead let's do define draw arm. It's supposed to get L1, L2. Well, we can't do L1 and yeah, all right. It's supposed to take these and it's supposed to also take X0, Y0, and XF and YF. Okay? It's supposed to take those and it's supposed to plot them. Now, of course, in order to get X1, you're going to need to call get point 1, L1, you pass L1 and theta, and X2, you're going to need to call get point 2, you can pass L1, L2, theta, and phi. Okay, now I don't want to write too much of the code for you, so I'm just going to create some dummy get point 1 and get point 2, where it's just going to return something simple, 2 and 1. It's just going to return 2 and 1. Of course, you'd want to implement those equations there to take the L1 and the theta and actually use them to return the right values. Okay, X1, Y1, X2, Y2. So then I want a similar function for get point 2. And let's make this 3, 3. Okay. And then I want this thing to plot that. So I'll do plot, plot. You recall we need to pass an array or a list of the x values I want and an array or a list of the y values that I want. Okay? And so I want to start at the origin, I want to go to point 1, and then I want to go to point 2. Start at the origin, go to point 1, and go to point 2, right? Everybody with me? And that's how we would build it in MATLAB. Start at the first 0 point, then go to the first point, then go to the second point. Okay? And so then in the main part of my function, I could go ahead and call draw arm, and then these are all just dummy values. They're not actually used. Although the x0 and the xf could be. So let's see, what was... xf was negative 4, 4. Negative 4, 4, that's what, somewhere around 3, 3. Well, you know what? Let's make that 3, 3, because then that's gonna point 2 is gonna start at that point. Yeah. Okay. Negative 4, 4. Okay. Let's see what happens here. Go here. Python. Boom. Get point 2 takes 2 positional arguments. 4 were given. That's because I copied and pasted and didn't add. This is supposed to take L2, theta, and phi. There we go. That doesn't look like. Okay, right. So starts at 0, 0, goes to 2, 1, and then goes to 3, 3. Okay? Now, we could also have it draw the magenta line. So perhaps I could go ahead and do a plot figure, open up a figure. I could do plot clear that figure, and then I can do plot.hold true. Then I could plot those, and then I could plot from x0 to xf, and from y0 to yf. And we'll make that magenta, and we'll make sure that that stays blue. Okay, so now I've got arm. There's my arm, my two positions of my arm, and there's my magenta line for the path it's supposed to follow. Okay? Everybody with me on that? Now I want to explain one interesting thing, different, a little weird about Python and the way matplotlib works with its figures. You'll notice that this figure ended up in this IPython console. Okay? But there's actually many different ways that you can run your Python program. You can run it in Spider like this. You can write it, you can do it in idle, which was the original way I was thinking we would do things in this class. And in idle, there's a separate window for the console. You know, they're all not together. There's where you type your script, and then there's another window for the console. Okay? You can actually run your program from the command line. You can run Python from the command line, and you can actually also double click on your py file. It's actually kind of like an executable. I did put it in here. Put it in here under Untitled 0, right? Here's the file, untitled0.py. And if I double click on that, it actually runs it in Python. It runs the Python interpreter and runs it. And you see it ran and it ended, but I never got any figure. Okay? And that's because there's, oh, I did not mean to click on that. When you run something in Python, you can run it in what's called an interactive mode or a non-interactive mode. And this IPython console is the interactive mode. And if you plot something with matplotlib in the interactive mode like this in this IPython console, the figure will show up inside of this. Okay? But if you run it in idle or you run it from the command line, that's in the non-interactive mode. And you will not see the figure because there's nowhere to put it. Okay? So if you want the figure to show up, you need to tell the figure to show. Okay? So if I do that and now go to here and double click on there, it opens up another window with my figure in it. That's the non-interactive mode. Okay? So if you were doing this in idle or many other types of Python IDEs, you would need to do that plot.show or else you'll never see the figure. If you're using Spider, you don't need to, but if you're using something else, you'll need to put the show in there. Just so you know, otherwise you might be pulling your hair out because you can't see your figure.
Would Spider just open another window?
No, I'm pretty sure if you do it in Spider, it has no effect. The show has no effect if you run it in Spider. There may be a way to force it to open a new window, but I'm not sure.
That would behave just like MATLAB, because it...
Yeah. Okay, so that plot.show might be important depending on what environment you're working in. Okay, so Kyle, did I answer your questions about that you were wanting to know about this problem too? Okay. So the idea is you're going to need to have a loop to loop through to change this position. So again, you're going to try 4 candidate positions. Throw away any that get you farther away from the goal, and then of any that are remaining, look which one is closest to the line. Okay? And closest to the line, that's why I have that function point line distance. There's this function here, point line distance. You pass to it a point and you give it a slope and an intercept of a line, and it will return for you the distance between that point and that line. Okay? Just like getLine, you pass to it 2 xy pairs for the points on a line, and it will return you the slope and y-intercept of that line. Okay? So for that magenta line, you're going to need to call getLine to find what is the slope and y-intercept of that magenta line. And then you can call for any particular candidate point, you can call point line dist by passing to it the point you're interested in and the slope and y-intercept of the magenta line, and it will return for you how far that point is from the line. I've already given you all the math and the equations that you need to do that. Okay? Even gave you the Euclidean distance. You're going to need to know how far is this candidate point from my goal, because I want to throw away ones that are farther away from where I currently am. So you're going to need that Euclidean distance. Okay? All right. Any other questions before we break and Wednesday folks go to lab? No. All right. Well, good luck on that. And let me know. Come on into office hours. They're laughing. Good luck. Let me know if you have any questions. I'll be happy to answer stuff in office hours or whenever.